Okay, off we go. So, real quick, as I've been announcing sort of periodically for the last 10 minutes or so, we are starting with attendance quizzes. The attendance quiz is up. It's available. It will disappear in about a minute and a half, right? So make sure to get that quiz in. This is the only way to get credit for attendance, okay? And having it disappear 2 minutes in is how I enforce punctuality, the requirement that you do have to be here on time. Okay, so enough of that. Make sure to get that done. Okay, so last time we were talking about graphs, right? Now this is what everybody's familiar with. You've seen that a million times back in high school classes. It's our old friend. We're so familiar with it. On some level, it's actually easy to forget what it actually means, right? Very easy to forget what it actually means. And so different ways to think about this, but you can think about this as we are making the choice to set the output values of the function equal to a new variable. Right? That's a pretty reasonable way to think about it. Another way to think about it is you can think of this as taking what you might call the domain. It's a little sloppy, but you know what I mean. And the formula for the value of the function tells you how far to push that up. Like so. It's equivalent, right? But different way of thinking about it, sort of different intuition. Okay, and if you just kind of copycat, do the same thing for a function that has now two input variables, right? So a two-dimensional domain. Notice that what you get is now a surface. In particular, you get a surface whose equation results from setting the value of the function equal to, again, a new variable. That new variable is now z. Okay. Has to be z because y is an input variable. Okay. All right. So, seems like a pretty good idea. We've got a nice construction. We're looking at a multivariable function. We're seeing a picture. The picture is even kind of reminiscent of our old friend, right? Here's the problem. We're kind of out of dimensions at this point, right? We're already drawing a three-dimensional picture, right? And it's a three-dimensional picture because the picture represents an equation that has three variables. There's two input variables because it's a two-dimensional domain. There's one output variable. That makes a total of three variables, thus three-dimensional picture, right? Okay, so let's just belabor what you probably speculated already. Let's think about what would happen if we had a function of three variables. Just three, right? It's not 17, right? Just three variables. And here's the thing: you say you want to form the graph. The graph is what you get when you set the value of the function equal to a new. Now that means fourth variable. And notice your resulting equation here lives inside of R4, and you can't draw that, right? It just doesn't make any sense. So the graph construction is kind of useless in this situation. This is a problem. It's a nasty little problem, all right? So if you might have had some instinct or intuition that, multivariable calculus is going to be a lot like single variable calculus, but, it's just kind of like this, height will always represent the value of the function. No, you can't. It's just not enough dimensions, right? So, nasty problem. We're going to have to come up with other ways to understand functions in a, geometric sense. So, other constructions. Very importantly, not the graph construction. Right? The graph construction's crashed and burned badly here, right? So, we're going to have other kinds of constructions that will help us have geometric intuition for what a function looks like. And that brings me to this boxed point down here, which is you really cannot conflate a graph with the function whose graph it is. They're different things. Not every picture we draw will be a graph. If you approach every picture as if it is a graph, you're going to get a lot of wrong answers. Right? Worse, you're going to have a lot of invalid reasoning. Right? So, that's the situation we're in. So let me show you some of these other types of pictures we can draw. These are not oh, by the way, related note. Some students are accustomed, you can get away with this in high school in most cases, and you can get away with this in most single variable calculus classes even. Most students are accustomed to using the word graph sort of interchangeably with the word picture. And that's a problem too, because not every picture is a graph, right? And whether a picture is or is not a graph is going to have very serious repercussions in terms of how do you make sense out of calculus, right? So that's a bad habit that everyone has to break themselves of. I had to break myself of that habit when I was y'all's age. So anyway, heads up, you're going to have to try to be more careful, more deliberate in your choices of terminology. So not every picture is a graph. Okay, here's I think a really nice point of view. I mean, let's look at we had a problem previously with functions from R3 to R1. Couldn't draw the graph. And here's one take on how to represent that. We've got a domain that's R3. So here's a picture of R3. I just draw the domain. Right? And then let's see, our target is R1. Okay, well, I'm drawing R1. I've literally just drawn the domain and the target, and then I literally represent, this action of taking points from the domain and sending images into the target. That action I literally just represent by way of something like this. So this is what I like to call the literal picture of a function. I don't know that if there is a more sort of agreed upon name for this picture. I don't remember ever seeing one. Anyway, I'm going to call it the literal picture. If nothing else, I think that's an accurate description. Okay, so for example, we can talk about, let's see here, let me get rid of the colors. We can talk about this point here. That's a point that's in the domain. And I can say, okay, what happens if I plug that point from the domain into the function? I get some output value. That output value will be in the target, and maybe it'll be a point like that. I mean, there is a picture of sorts. Right? Now, I'll bet you're disappointed. Where's the shape? How am I supposed to understand the function from the geometry of what I'm seeing here? I don't see slopes. I don't see curves. I don't see concavity. Wow, how is this useful to me? Right? And that's a reasonable gripe. I will point out, for whatever it's worth, I mean, beggars and choosers and all that, I mean, this disappointing picture, I think, still gets the win over this complete 100% failure to draw any picture at all. Right? Something's better than nothing. So already, I think we have to confess this is better than the graph would have been. The non-existent picture of a graph. Okay, now let me try to persuade you, though, that there is still something even more valuable about this kind of picture, and that is, let's entertain a scenario, a particular situation. So, we've got some function, whatever. And I'm at this point A in the domain, and the image is this value f of A here in the target. And now, let's suppose that from this point A, where I like to think of myself as being, right? What if I start moving? Well, okay, well, how would I represent movement? Well, when you move in a direction with a certain speed. You could represent the speed with a magnitude. We could use a vector, right? This is a pretty reasonable way to represent a velocity. And, okay, well, what would be the result of me, having started at this point, but then moving with some velocity? Now I'm going to just appeal to your, let's call it algebraic intuition. If you were in the process of changing what you put into the function, hopefully no surprise, that will change what comes out of the function. Said differently, movement in the domain will cause some sort of movement in the target. And one of the things we're going to do, give me 2 seconds. One of the things we're going to do in this class is we're going to talk about, well, how can I understand this output velocity given that I have some corresponding input velocity. It's something that's going to, well, a related term is called directional derivatives, and we'll get to that in a bit. But the point I want to get to now is this scenario, this very natural scenario, I can represent with a picture in this context. I think this is a really compelling argument for why having this literal picture, disappointing though perhaps it is, right? Still, that's got some value. Yes.
How are you sure that's positive?
Oh, I just made it up.
Okay.
Yeah, no, I mean, so that's ultimately a complicated question. We're going to have to understand, in some sense, how to take derivatives or something of this function f. And it's actually going to take us several days to build up to how to compute these. Yeah, so this was just a for example. Yeah. Okay, so there's a useful picture. Heads up. By the way, very common in math. Again, weird. It only recently occurred to me, weird that it doesn't seem to have a well-established name, but it's a very common kind of a picture to draw. Very useful. Okay, next kind of a picture. Not a graph. Level sets. Now, there's a bunch of how do you write that down formally? Okay, this is the formal definition of a level set. Let's get right to the examples. I think the formality here is it's more trouble than it's worth. But the big idea of a level set is you pick an output value. So let's suppose that I pick this output value 1. And then I ask the question, what are the corresponding input values? What are the corresponding points in the domain that the function sends to that exact chosen output value? All right, so we call this a pre-image. It's denoted. Actually, let's take a look at this notation now that we've got a picture. So we call this f inverse of b. Oh gosh, let's see here. Call this f inverse of b. Whatever this value is here, that's our b. And notice we're just going to take that b and we're going to look for what are the points in the xy plane. What are the points in the domain that when you plug them into your function f, give you that chosen value b. Right? So anyway, that's all this notation up here means. Reasonable question, hey, how come we call this f inverse? Hey, wait a minute, is that function even invertible? Can we talk about f inverse if f, we haven't even established if it is invertible? By the way, this function here, not invertible. Right? You should be a little uncomfortable with the idea I'm calling this f inverse. Right? It's just a notation. It does not mean the inverse function in this case. What it means is, look, we're going to kind of turn this around. We're going to kind of go backwards. And the backwardness is, you give me a b, and this process produces a set in the domain. But the given is over here. The result is over here. And so in some sense, there's a backwardness to it, even though the function's not invertible, and that does not mean the inverse function. But thus the notation. How we doing? Everybody all right? Okay. All righty. So let's look at this particular example. And let's see here, for this output value, we're going to look at f inverse of 1. Well, we're looking for the set of points where the value of the function is equal to that output value 1. Okay. And so the result, the level set that we associate to 1 is the curve that has this equation, x squared plus y squared equals 1, and of course we recognize that as being the unit circle. Yes?
So are we, what's the dead giveaway between being asked for the inverse of a function versus asking for kind of the reverse?
So how do you know in whatever context what this is supposed to mean? So in the case where f is invertible, the level set that we denote by f inverse of whatever, that level set will be a single point, and that single point is the value of f inverse. So there's no contradiction, right? So if it's a set, then it's a set. If it's a point, then it's a point. It just is what it is. And so let me answer that a little bit differently then. You can interpret that as the inverse function if you are willing and able to go to the trouble to check that the function's invertible. But there's no contradiction to worry about. Does that make sense? How about anybody else? All right, now, so this is a level set for this one value that gives me one curve. But notice we can plug in different output values, set the function equal to those different output values, and we get a different curve. Right? And you can do this for as many output values as you like. I just did it for 2 of them here. I got 2 curves. But I could do it for 10 output values. I would get 10 curves. The more outputs you pick, the more level sets you draw, the better kind of an understanding, better sort of a geometric representation you'll have, of the function. Now, what does this mean? What does this picture tell me about that function? Do the slopes of these lines tell me something about the derivative of this function? No, that's for graphs. That's calculus of graphs, right? This is not a graph. You can't talk about calculus of graphs. So how to interpret these pictures is, well, we're going to have to kind of think that up. We're going to have to make a new geometric intuition as we go on, right? And roughly speaking, I mean, I like to think of, in some sense, as I go from one level set to another, well, the values of the function here, well, see, this one is where f is 1, and this one is where f is 2. So as I go in that direction, apparently the function's increasing. Now, arguably disappointing. Hard to admit, I feel like I've got a less complete picture. I could draw the graph of this function, by the way. Right? It's only 2 input variables. We could draw the graph. Feel like the graph tells us everything, like we can see the whole graph. Here's the problem with graphs. If I were to draw the graph of this function, let's look back at a picture that we already have of a graph of a function of 2 variables. And you feel like you're seeing everything here? That's an illusion. Right? I didn't draw anything at all in here where that's red. There's no drawing there. You don't know what's going on there. I didn't give you any geometric indication at all of what the function's doing in there. I fooled you into thinking that I showed you the entire thing because the way these edges curve, you feel like you're kind of seeing a surface in there, but I didn't draw it. So there's gaps in this picture too, right? If you're drawing on 2-dimensional paper, graphs and level sets both have this same kind of disadvantage of we can't really see the whole thing. So that's the fault of the fact that we have 2-dimensional paper, 2-dimensional screens. It's not the fault of the construction. Okay, a couple of examples. Y'all have probably seen this idea called contour lines. And the idea of a contour line is that every point on, let's say this curve right here, every point on that curve has the same altitude. If you're out hiking or something like that. And so this is a map, sometimes called a contour map or a topographical map. So contour lines, if you think about it, in fact, then are level sets. They represent a constant value of this function called the altitude function. So contour lines are level sets of the altitude function. This is a great way to develop intuition for level sets. In fact, most of the time when I look at level sets, in my mind, I'm thinking, okay, well, these are the contour lines of some map, and I've done a teeny tiny itty bitty little bit of hiking in my day, and I've seen topographical maps, and I have some instinct for, oh, that looks pretty steep. Going, let's see here, going, for example, along in there, like if I were to hike like so, that's going to be a steep climb along in there. And when I was y'all's age, I would have been all gung-ho and excited. Let's do it. Let's head straight up that mountain. Right? And nowadays, I'm thinking, okay, you know what? How about this? How about we kind of slowly wind our way around like this? A lot less steep. Does that make sense to everybody? So I'm making geometric use of this level set construction. It's helping me to plan my hike. Right? I'm not going to cross lines that are close together. You're telling me I'm going to gain 100 feet of altitude over that much distance on the map? That sounds really steep. I would much rather gain that same 100 feet of altitude over this much greater distance, right? And keep that steepness down. Thank you, level sets, right? Level sets help us make this determination. Everybody on board? By the way, my shirt is a topographical map. I thought that was fun. It wasn't even a special order. They just had them at the store one day. Okay. Well, for your amusement, they have topographical maps on government website. I've already forgotten. It's like the U.S. Forest Service or something like that. And you can download real topographical maps. This is the official USGS map of a particular mountain in Colorado that I have successfully hiked in my youth, way back when. And a couple interesting things about it. I will draw your attention to how close together the lines are right here. Look how, they're really densely, they're packed in there. That means there's a lot of altitude change happening over a very little bit of horizontal distance. And the reason they're that close together is that's the edge of a cliff pretty much. It's about that steep, right? And if you fall, you will not stop falling for about 1,200 feet, right? So it's very scary. If you're standing right there, it's unsettling. So that's interesting, I think. I will also point out, I think this is a cool observation. Check out how the trail is all zigzaggy right there. Why would they do that? Well, because it allows you to take the same amount of altitude gain and spread it out over a greater horizontal distance, right? So instead of heading straight up the mountain, let's do what they call switchbacks, right? And you kind of go largely horizontally, just slowly zigzagging your way up the mountain. That's a much more reasonable thing to do. And when you're at, 12,000 feet, air is gone, right? You really notice. It makes it a lot easier. So, okay. Alrighty. Okay, so here's an interesting observation. No big deal. You may have noticed the way we make a graph. Oh, whoops, I wanted to be in the highlighter mode. The way we make a graph is by setting the value of the function equal to a new variable. The way we make a level set is by setting the value of the function equal to a constant. The difference is a variable versus a constant. So I'm going to make the innocent observation of if I were to then subsequently set that variable equal to a constant, right? In other words, if I were to take the graph, and if I were to set z equal to a constant, now again, geometric appeal, this is what it looks like when z is a constant. It's a horizontal plane. That means I'm effectively taking a horizontal cross-section. If I set f equal to z and z equal to c, in effect, I have set f equal to c. So in fact, and I'm going to say this deliberately sloppy. I will fix my sloppiness in a couple minutes here. But level sets are horizontal cross sections of graphs. Really nice little connection. Does that make sense to everybody? Everybody on board with how I connected those dots? Okay. Let's see an example. Here's a function we've talked about before. Right, now on the one hand, I can take that function, I can set the, I've already forgotten what colors I used. Level curves in blue. Okay, so we can set that equal to various constants. Look at the resulting equations. It gives us various circles. Those are the level sets. Same function now, exact same function. Let's look at the graph. Right, so level sets we get by setting the function equal to a constant, different constants. The graph we get by setting the function equal to a new variable, now z. And I'm going to ask for your flexibility. Trust me for a minute. By the way, we're going to justify this later today, depending on if I go fast enough. Certainly very soon. I have not yet given you the tools to know how to draw a picture of the solutions to this equation, namely the graph of this function, but it ends up being that it's a bowl like this. And again, we'll justify that very soon. Okay, so we got level sets, we've got a graph. Let's take a moment to recognize, oh my gosh, totally different pictures. Both representing the same function. It's the exact same function. Just representing it with two different pictures. Seemingly unrelated pictures, except that we did already make this observation that if I take horizontal cross sections, notice that the horizontal cross sections, again, that you get by setting z equal to whatever various constants, those horizontal cross sections are, check it out, circles. In fact, those same circles. Is that cool? Are you happy with that? Okay, now let me fix my crime, right? My math crime. I said that these are in fact the same. They're not quite exactly let me just. Oh man. Okay, let's do it like this. So here are the level sets. Here are the horizontal cross sections of the graph. You see what I mean when I say they're the same. Okay, yeah, but technically, the level sets live in two dimensions. They live in the domain. Level sets always live in the domain. These are curves in the XY plane. Two-dimensional points on these curves have two and only two coordinates. These are circles floating in space. Points on these curves have three coordinates. So technically they're not quite the same. Now again, okay, yeah, but come on, the z coordinates are just the constants that sure, we can explain it away and we can ignore those z coordinates, absolutely, right? But it doesn't roll off the tongue quite as well if you get fussy on this point. So I like to leave it as a sloppy but pithy statement that level curves are horizontal cross sections of graphs. Okay. All right. Okay. Yeah. Got to be careful. You really got to be careful. We're going to learn over the next few weeks. Anyway, how long is this semester? But anyway, let's see. In some sense, over the next month at least, we're going to be learning calculus of multivariable functions, right? But how we interpret the algebra that we do. In other words, what does this mean geometrically? Depends dramatically on what kind of picture you're looking at. Right? So here's an example, and there's details that y'all can think through for yourselves. I'm going to hit some highlights on how I came up with these functions, but the big point I want to make is that this one line described by this equation right there, given equation, that is a graph of a function. It is also a level set of a different function. And, by the way, flashbacks to Chapter 1, we've talked about how to parameterize lines. So this is, in a way, represented by this third function, namely the function that parameterizes it. Okay. Which is awkward grammar. So, for FYI, the curve that is parameterized by a function, you'll notice it's literally just the points that come out of this function, and we already have a name for that. That's image. Right? So this is the image of this parameterization down here. Okay, so this line is three things. It's a graph, it's a level set, and it's an image. Three different functions, f, g, and r. In different ways, the calculus of these three functions all will tell us interesting and useful geometric information about this curve. But what information it tells us and how it tells us that related to which kinds of derivatives of which of these functions depends on, wait, are we talking about the one for which it's a graph or the one for which it's a level set? You've got to know what construction you're talking about. Otherwise, you're going to get some silly nonsense answers. So, for example, how would I find the slope? How would I find the slope of this line? And it's very tempting to say, well, slope. That's the derivative of the function. Which function? Is it the derivative of this function? Nope. This idea that derivatives give you slopes of the curve is part of the calculus of graphs, right? It is because this function's graph is the curve that its derivative gives you the slope. If you were to take some sort of derivative, whatever that would mean, we haven't even talked about derivatives yet for a function of two variables, but if you were to take some sort of a derivative of this and cite that as telling you the slope of this line, garbage. Nonsense. And again, I emphasize it's not just that you'll get the wrong answer, it's that your reasoning doesn't make any sense at all. It doesn't hold any water. It's just nonsense. Right? So, the way I like to phrase this is every one of these constructions has an associated calculus. This idea that slope is the derivative, that's part of the calculus of graphs. We will talk about the calculus of graphs in a couple of different ways. There is a completely different analysis that will go into producing something y'all very likely haven't seen before. There is also a calculus of level sets, and it is completely different from the calculus of graphs. And there is a calculus of parameterizations as well. So you got to be really, really careful. Again, depending on what you're interested in, you got to use whatever is the appropriate function for whichever kind of calculus you would like to make use of. And if you apply the calculus of graphs to this function here, nonsense. Okay. All right, so let's talk about how to find these functions. Let's see here. Some of these are kind of easy. How did I come up with this function here? Well, I know that I want to take a level set of something, and when I take the level set, I want to end up with this equation. Let me say that differently. I want some expression that when I set it equal to a constant gives me this. And so I just think to myself, hey, check it out. That's pretty easy. There's a function that when I set equal to the constant 6 does give me the equation I want, right? So that's sometimes it's right there looking at you. That's nice. Does that make sense to everybody? Okay. All right. How did I get this function here? Where did that come from? Well, let's talk through it. I'm looking for something that when I set it equal to y will give me that equation. This is not currently written as y equals. So I want some function of x that I can set equal to y, and I want to get this. Okay, so what I'm going to have to do is rewrite this until it says y equals. In other words, I just need to solve for y. Right? So very nice little pithy punchline there, and if you were to take this y right here, solve for that y, what you will get is this, or if you'd like, said differently, this is the thing that when you set it equal to y, again, that's how graphs work, will give you that equation. Is that cool? Okay, yes.
I think for every like one of the R things, you can either choose to make it one of the variables in the that's given, or like make it.
Yeah. That's right. So I could have solved for x, in other words, for example. Yeah. So yeah, you do have a choice sometimes, right? So if I can solve for y, then I can view this as a graph, specifically where y is a function of x. Or if I could and chose to solve for x, I could view this as being a graph in sort of a different sense where x is a function of y. Absolutely.
But then for like the level set, so you can either make it an R2, like you can set it all equal to a new variable as well.
Well, now this does have to be, we are kind of stuck with this being two-dimensional. Because this is an equation of two variables, and we can't really do anything about that. But we do have some options down here. So obviously, if I set this equal to 6, then that gives me that. But if I wanted to, I could rewrite this function as 2x plus 3y plus 1. New function. Now I changed what g is, but I can still make that curve a level set of this function by just setting it equal to a different appropriate constant. And again, that is equivalent to this. Yeah. Is that kind of what you were getting at?
Like, yeah.
Okay.
Thank you.
Okay. Anybody else? Feel free. Okay. So yeah, there's different ways. You got some flexibility in some of these. And flashback to chapter 1, we already talked about how to create parameterizations. Make sure you can still do that, right? By the way, this is not the only function that parameterizes this line. There's lots of different parameterizations. You don't have to produce exactly this parameterization. But make sure you can produce a parameterization. And just for fun, you might want to ask yourself, how would I construct this one specifically? Something to think about. Okay, so yeah, so be careful about this. By the way, if you look through my old exams, you will find many examples of old test questions that are almost exact rip-offs of this example. I think these are excellent test questions. Now, I want to warn y'all about one thing. It is tempting to look at this and think, that's Algebra 1. I did that in 7th grade, or I don't know, whenever. I don't know when that happens these days. But it's very tempting to think. The scariest thing that happened here is somebody divided by 3 at some point, right? This looks trivial. It's not. The mechanics of the algebra very often is pretty easy, absolutely. The tricky part here, what makes these questions challenging, is you have to use the terminology strictly, right? If I ask for a function whose graph is this line, and if you give me, well, let me say this differently. If I ask you for a function whose level set, one of whose level sets is this line, and if you write down this equation, that is not a function. That's not a function for which one of the level sets is that line. That's an equation representing one of the level sets. The equation is produced from the function, right? The function is this thing right here. Or, again, let's be careful about it. Functions are trios, right? This is the function. This is a function which, if you apply this process called constructing the level set, will give you the line that we wanted. So that's an important distinction, right? But in some sense, the whole point to all of this is we don't want to conflate functions with the different kinds of pictures that I can view them with. So if you do conflate them, again, it kind of misses the whole point of the question. Does everybody see what I'm talking about there? Does everybody see how these are not the same thing? right? So again, you gotta be careful. Interpret the terminology exactly as you're supposed to. That's what makes it hard. That's why a lot of students will miss points on these questions, is they give me stuff that isn't right. Right? Or here's another so close but problem. If a student, again, find me a function for which one of the level sets is that line, and then the student writes g of xy equals 2x plus 3y equals 6. Again, if you write this down, let's see here, you write this down, you're telling me that, among other things, g of xy is equal to 6. And no, it's not. It's equal to 6 at certain points that I'm going to be subsequently interested in, but that's not what the question asked for. That's a problem, right? That's importantly wrong. So these are the kinds of subtleties you have to be careful about, right? So think it through. Make sure you're comfortable with my gripes about these first two examples that I just talked through, right? If you're not clear on why I'm upset about those little things, right, come talk to me. I'll be very happy to explain. Office hours, this would be a fabulous thing to talk about in office hours. But make sure that you are comfortable with all of the little fine distinctions here, and then on questions like this, that's what you need to be really wary about, right? Make sure you're interpreting the terminology as written and that you are using the terminology appropriately. Okay, we already talked through all of that. Here's a good little trick, nice little fast one that you can pull. This algebra right here is surprisingly useful. Again, the algebra is trivial. All I did is I took some stuff that was on the right and I subtracted it over to the left. Again, don't make the mistake of thinking, I could do that in 6th grade, right? That's not the point, right? The point to this algebra is it allows me to take something that came to me as a graph, and I have now rewritten it as a level set. Who cares? Why would I be interested in such a thing? Well, sometimes when something comes to you as a graph, for whatever reason, sometimes, but the thing I want to compute is something that, oh man, I wish I could use the calculus of level sets. And if you find yourself in that situation, this is not rare, right? You're like, I wish I could apply, but I'm not allowed. I'm not allowed to apply the calculus of level sets to a graph. Again, nonsense, crash and burn. It doesn't make any sense at all. Well, if you can turn a graph into a level set, you absolutely can apply the calculus of level sets to this level set, and that's fine. Right? So this opens doors. This makes more tools available. Now, we do have to be careful. What functions are we talking about? Yes, what I have in purple is a graph, but it's a graph of that function. And then I say, well, it's also a level set. Okay, yeah, it is also a level set, but very importantly, it's a level set of a different function. Really importantly, different function. F is not the same thing as y minus f. They're different. Right? Different number of variables, if nothing else. This function up here has no y's in it. This function down here, very importantly, has a y in it. And so you got to keep track of what the different functions are, how this little fast one changes what function you're working with, right? But aside from that, it turns a graph into a level set, and that's pretty cool. Here's a really quick little example. We've already seen, again, this function. We can talk about its graph by setting it equal to z. Maybe for whatever reason, I'm interested in some geometric property of the graph. Right? Maybe the fact that I need to look at the graph may be imposed upon me externally somehow. Right? If I want to learn something about the graph of this function, well, you'll notice all I did here is I pulled the same exact fast one that we did up above. Nothing happened. I just moved a couple of terms around, right? But I can learn about that graph by looking at the calculus of level sets of that function G. That makes sense to everybody? And if you apply the calculus of level sets to the original function f, you get nonsensical garbage. Got nothing to do with the question. Is that cool? So little subtleties, right? The devil's in the details, and you gotta be careful, right? Watch out for those little detail devils. Okay. So this is a really nice fact. Every graph is a level set. Again, that's the little move that shows it. You give me any graph, I can move terms around, make it a level set. Just be advised, it doesn't go the other way. Not every level set is a graph. Here's an easy counterexample right here. I'm taking a level set. That's a level set. And it's just not a graph. I cannot solve for y as a function of x. I cannot solve for x as a function of y. Don't get me wrong. I can do a little algebra and I can write y equals, and then I can write some stuff after that, right? But that's not a function. To be a function, if I want to interpret y as a function of x, I need to have exactly one output value per input value, and that whole plus minus thing makes that all messed up. Okay, so crash and burn. If you try to rewrite this level set as being a graph, too bad. Doesn't work. And for whatever it's worth, we're going to revisit this question in a couple of weeks. We're going to talk about something called the implicit function theorem, where we're going to recover kind of a partial victory out of this loss. But for the moment, the answer is just no. How are we doing? Everybody's good? Okay. All right, so here's a nice observation. I think ultimately this is a pretty straightforward observation, but it's a little, you got to think it through. There are some equations, and I emphasize, not all equations will do that, right? This is a special case. This is a kind of narrow-ish consideration. But if x and y appear only as part of this expression, that happens sometimes. Sometimes there are the only ways that x and y show up in your equation is as part of that expression. When that happens, immediate, valuable conclusion, that surface is rotationally symmetric around the z-axis. So I love it when stuff like this happens, when you have something that you can notice by casual inspection at a glance, and then you get a nice payout, right? Nice, valuable geometric conclusion that will help you draw the picture, will help you understand the object you're looking at, as a consequence of a quick observation. So the reason this works is because of for such an equation, let's think about these 2 points. There's that purple point, and there's that red point. This is what you get when you rotate the purple point around the z-axis. That'll get you to that red point. Well, here's the thing. Notice these 2 points, they're different points, but they have the same value of r. Square root of x squared plus y squared, let's call that r. They got the same value of r, they've got the same value of z. The equation only depends on this expression of x and y, for which these 2 points agree, and z, for which these 2 points agree. So if either one of these points satisfies the equation, so does the other one. And if either one of these points fails, so does the other one. And so, therefore, all points that are rotations of each other either all work or they all fail. This surface is rotationally symmetric around the z-axis. Does that make sense to everybody? It's a cool little argument, yeah.
Do you need the square root, or is it just the x squared plus y squared?
Because there are, you can make a version of this without the square root, but it's a little bit more careful to have the square root in there. Yeah, there's some nasty little issues that can come up. I think this is going to be easier for us in the long run. So let me show you an example, and I'm also going to show you, okay, a little ahead of myself, but momentarily I'll show you how this doesn't, the square root's not going to matter to us anyway. Real quick observation before we do that, let me also point out, another way to think about this is if you have an equation that has this property, and if you were to rewrite in cylindrical coordinates, let's think about what that cylindrical equation would look like. I claim there won't be any thetas in it. Can't be any thetas in it. Where would the thetas come from? The thetas would have to come from like x or y. But wait a minute. X and y only appear as part of this expression, which is r, which has no thetas in it. So any equation like this, there simply straight up will not be any thetas, and we've already talked through if you have a cylindrical equation with no thetas, it's rotationally symmetric. Okay, so where this is useful, let's look at this equation right here. Notice it fits the proper form. Now you object about the square roots, but notice I can rewrite this as z equals the square of square root of x squared plus y squared. Right? So in effect, for our purposes, yes, this equation does involve x and y only in that allowed form. Is that cool? Okay. Okay. So I immediately know that this is rotationally symmetric around the z-axis. And now I'm going to make a geometric appeal. If I know it's rotationally symmetric around the z-axis, all I have to do is understand its cross-section. Pick any plane you like, whatever. Any plane that contains the z-axis. Doesn't matter. If I know what that cross-section looks like, and if I know that it's rotationally symmetric, that one single cross-section, I can just rotate that one single cross-section around and it will produce the rotationally symmetric surface. So how do I know what that curve is? Well, pick your favorite plane containing the rotation axis. I'm going to use x equals 0 for no particular reason. Plug that in. See what comes out. You get z equals y squared. Now I already know what that looks like. That's just a parabola. Good old algebra 1, algebra 2. I don't know, something like that. Algebra 1, algebra 2. So that means this cross-section's a parabola. That means that the surface that I'm actually interested in here is whatever you get when you take that parabola and rotate it around the z-axis. In other words, you get a bowl like we previously argued 20 minutes ago. Does that make sense? Everybody see how this process, where there's a really cool process, we turn a three-dimensional problem, effectively we turn it into a two-dimensional problem by making this rotational symmetry argument, and we know how to do two-dimensional problems, and hop, skip, and a jump, we win. Okay, good place to draw the line. We'll pick up here on Friday. See you later. Thank you.